Welcome to Space Oddities, and especially welcome to this short presentation on spectroscopy. When you get astronomers talking, it's very rare that the words spectra, spectroscopy or spectrograph will not appear. This is not a surprise, as spectroscopy is one of the sharpest tools in an astronomer's toolbox when he is looking at the mysteries of the universe. Before we can talk about spectroscopy, we first have to look at light as a whole. The light that we detect with our eyes comes from our nearest star, which is the Sun. The light we see with our eyes travels the 93 million miles from the Sun to the Earth in 8 minutes and 20 seconds. The light arrives to us in little parcels of energy called photons. Now these photons all have varying energy values, and this decides their wavelength. And that's all I'm going to say on photons. If you want to research them more, then you can do at a later date. For now, all we need is that the energy contained in the photon decides its wavelength. Remember that for later. Right, the full range of light is huge, and as I said, the wavelengths vary a lot. Here is the spectrum of all light, and as you can see, it goes from very low energy waves, which are radio waves, all the way up to the high energy waves, which are gamma rays. For today's purpose, we're going to be looking at the visual light. As you can see, the visual light sits on the spectrum, which is known as the electromagnetic spectrum, just above halfway. It covers a very small part of the spectrum. As I said, the photons are little packets of energy, and they vary. And we can see this by using a very simple experiment, an experiment that you've probably did at school. And that is using a source of light and a triangular prism. If you pass the light through one side of the prism, it gets bounced around 2 or 3 times inside the prism due to the angle of the actual facets, and then it reappears the other side of the prism, and you can project it onto a screen. Now as you can see, you will find a lovely rainbow effect, which stretches on one side from red to the other side, which is blue / ultraviolet. This is showing you the different values of energy in each of the photons. We can test this theory by placing the sensor of a thermometer in the red light, and it will read a temperature. If you then move the sensor to the blue or ultraviolet light, you will see that the temperature is actually higher, because the photons at that end of the spectrum are carrying a higher energy, whereas in the red it's a lower energy, hence the lower temperature. By performing this experiment, you are in good company. Isaac Newton himself used to use this system to split the light into its constituent parts. So a quick recap so far. The low energy photons with long wavelengths sit at the red end of the visual light spectrum, whereas the high energy photons sit at the blue end with their shorter wavelengths, and all the wavelengths in between give us the different colours of the rainbow. Also, visual light is only a very small part of the whole of the electromagnetic spectrum and sits halfway along. So, back to our original questions. First, what is a spectrograph? A spectrograph is an instrument that separates the light from a star or any other light source into its constituent colours or wavelengths. So it's a bit like the prism we mentioned in the experiment earlier, but gives us the spectrum in a far greater detail. Question 2. What is spectroscopy? Stellar spectroscopy is the analysis of the lines in the spectra of stars, and is by far an astronomer's most important tool for investigating the physical nature of stars. So a spectrograph will give us the spectra of a star, but in far greater detail, in the form of little lines. And the study of these lines in the spectrum will tell us a lot about the star and its environment. So what can we see in this extra detail? We can see the radial velocities of stars, that is, motion of the star towards or away from Earth. We can calculate relative masses, orbital periods, and orbit sizes of stars in a binary system. We can measure temperatures, atmospheric densities, and surface gravities of stars. Also deduce magnetic fields and their strengths on stars. We can glean the chemical composition of stars, what atoms are present and in what states they exist. We can also watch the sunspot cycles, or should we call that star spot cycles. In that list I mentioned surface gravities of stars and also magnetic fields and their strengths on stars. Well, I'm not going to go into these because I consider this more advanced spectroscopy, and you have to use methods like the Zeeman effects and the Stark effects, so we'll leave that for another day. So back to these lines in the spectrum that give us all this information. The lines we see in the spectrum appear either dark or very bright. The dark lines are called absorption lines, while the bright lines are called emission lines. For our purposes, and to make it easier for me, I'm just going to talk about the dark lines that we see, the absorption lines. So what are absorption lines, and how do they get there? Well, to explain this, I must rewind the clock on the life cycle of the photon. The photon is first produced in the centre of the Sun, and it spends probably the next 100,000 years trying to escape the Sun. But in the centre of the Sun there is so many high energy particles that it's being buffeted around, ricocheted, ping-ponged all over the place. But eventually, if it's lucky enough, it will reach the outer layers of the Sun. Now in the outer layers of the Sun are all the elements that the Sun is producing, and also the elements that were present in the star's maternal gas cloud that gave birth to it. Remember I said each photon carries an energy level, which in turn determines its wavelength. Different energy levels, different wavelengths. Now the elements in the outer layers of the Sun are in a state we call ionized. This is where, when an element is exposed to high energy levels and heat, the energy levels and the heat will actually start to strip away electrons from the atom. For example, let's have a look at iron atoms. If an iron atom is in an ionized state, it will carry an energy. So again, it will have its own wavelength. Now, the photon, which is running the gauntlet of all these elements in their ionized states, if it happens to meet an ionized iron atom, which has the same wavelength as the photon, then the photon will be absorbed. And all the other ionized iron atoms with the same wavelength will also be absorbing all the photons with the same wavelength. This results in a deficiency of photons at that specific wavelength actually leaving the Sun's surface. This means when we project the spectrum onto a screen, you will see lines where the photons that have been absorbed are missing from the spectrum, and hence you get your absorption lines. And this tells us that iron at that specific ionized state exists in the Sun's outer layers. On this slide you can see the absorption lines for different elements. But we can also take this one step further. Let's get back to our iron atom. If the iron atom is exposed to higher energy levels and larger heat temperatures, then more of its electrons will be stripped. With the loss of each electron, it will exist in a different state. These ionized states of the iron will be betrayed in the spectral line also. They will be producing their own absorption lines. So what is this telling us? Not only is it telling us that iron is existing in the outer layers of the Sun, but also it is existing in several ionized states. We can see this in the spectral lines. So that also means that the outer layers of the Sun are at different temperatures in different areas, so that these ionized iron states can exist. If the Sun's outer layers were all one uniform temperature, we would only see one ionized state of iron. So the temperature varies over the surface. Job's a good 'un. There is a way we can test this. If we go back to the prism experiment we talked about earlier, but this time between the light source and the prism itself, if we place a test tube full of hydrogen and then pass the light through the test tube, then the prism, and project the spectrum onto a screen, you will actually see in the spectrum definite black lines. This is the spectral fingerprint of hydrogen. These element fingerprints in the spectra of the stars tells us so much about the star and its environment and where it actually came from. But I also mentioned that we can actually detect movement by again looking at the absorption lines in the spectra. We do this by using a method which is the light equivalent of the Doppler shift. Now the Doppler shift we've all experienced. It's when an emergency vehicle is coming towards you with its siren going. As it moves towards you, the pitch gets higher and higher. But as soon as it passes you, the pitch gets lower and lower. This is because as the vehicle comes towards you, the sound waves are actually compressed, increasing their frequency. But as it passes you, the sound waves become stretched, giving them a lower frequency, so the tone drops. Well, light acts in exactly the same way. If a bright object is moving towards you, the light waves actually get squeezed, increasing their frequency, which means the whole shift is towards the blue. If an object is moving away from us, the light waves actually get stretched, and the spectrum moves towards the red. This is called the red/blue shift, and it tells us which direction an object is moving, away or towards us. So what do I mean about red shift and blue shift? It means that when we look at the absorption lines in the spectra, if an object is moving towards us, the whole of the absorption lines will move towards the blue end of the spectrum. If it is moving away from us, the absorption lines will slip towards the red, and this indicates which direction it is moving in comparison to us. But this can be taken one step further. We can also, using exactly the same technique of the red shift and the blue shift, detect small wobbles in the stars themselves. Also, it will tell us if a star has a companion, and by watching their separate orbits, by using the red and blue shift, we can determine their size, their orbital lengths, and their masses. And all this can be discerned from the red and blue shift of the stars. Sunspots will be betrayed by the effects they have on the surface of the star themselves, and by looking at the elements and the states of ionization they are existing in. Also, spectroscopy can be turned towards nebulae and galaxies, again looking at the interstellar medium between all the stars, telling us how old the galaxy and all the elements that exist within the interstellar medium. And all this just from looking at a few black lines on a spectrum of a star. Well, I hope this makes it a little bit simpler for you if you didn't know anything about spectra. And keep an eye out for more of these jargon busters. Hopefully there'll be a few more on their way. Remember, you will find us on Monday nights at 8 PM UK time. Come and join the panel, and if you have any questions, drop them in the chat and we'll answer what we can. So I hope to see you soon there. Just before you go, just one more amazing wow fact. Now, we all know the universe started with the Big Bang, and not long after the Big Bang, in cosmological times, the universe cooled enough to actually form the first atoms. The first elements formed were hydrogen at 73%, followed by helium at 25%, and a tiny splattering of other elements. This hydrogen produced so early in the universe's history is all the hydrogen it is ever going to have. No more will ever be made. Now, our bodies are made up between 55 and 75% water. Now, water is 2 hydrogen atoms connected to 1 oxygen atom. So just think about it. The atoms that are going to make up your body, some of them are almost as old as the universe itself. Isn't that amazing? It's a bit of a wow factor, that. Anyway, we'll hope to see you Monday nights. Everybody please take care, and I'll speak to you soon. Bye for now.